Welcome to the METALLICO webinar on how LCA can support innovation in minerals and metals production. I'm Ramona Simon from the KIMA. I work there as a scientific project manager, and together with my colleagues Jana, we are responsible for the communication and dissemination of METALLICO. And today we have the workshop on LCA and how it supports in research projects. We have organized it together with UNITO and Politecnico di Torino from the University, our project partners. And yeah, we are very excited to give you more information on this topic in the next 2 hours. So before we start into the talk and into the presentations, we will give you just some technical advice. So as you have maybe realized, your microphone is muted today. So if you have any questions, please put them into the chat in the Q&A tool. It looks like this. And if you have a question specific to any speaker, please put in front of your question a short and then the name of the speaker, so that afterwards in the Q&A session we can see to whom you have directed these questions. Also, we would be very pleased if you put on your camera, especially during the Q&A sessions, so that we can interact more with each other. And if you don't like to be recorded with your camera, then of course you can also put it out. So this was with the technical recommendations, and I'm very happy to announce the first speaker, but also the chair of the session, Gian Andrea Blengini. He is holds a master, has received his master in mining engineering from the Politecnico di Torino, from Italy, and has a PhD in the earth resources from TU Lisbon, Portugal. Presently, he is a full professor at the University of Turin and co-affiliated to the Politecnico di Torino. He leads the Life Cycle Assessment Research Group and lectures on life cycle assessment and resources and environmental sustainability to undergraduate students, master and postgraduate level. He is also a principal investigator at the Joint Research Center of the European Commission in Land Resources Unit from October 23 to October 2021, and has the role of team coordinator in projects and activities. He also supports in the European Commission raw material policies with a focus on critical raw materials and monitoring of the circular economy. Moreover, he also targeted to the EU raw materials knowledge base, including the life cycle inventory data availability, coherence, and quality. I'm very happy to have this workshop together with you, and also for the many organizations you made. And yeah, thereby I want to share the floor with you. Thank you very much.
Thank you, Ramona, for this very kind introduction, a very long one. So I think I now have to speed up to save time, because we have a very packed agenda for the day. We have a lot of speakers and presentations. Let me first share my screen. I thought I was already doing that, and then let me go to the full presentation mode. Meanwhile, I saw in the chat that somebody was complaining that they could not hear us. I hope this is not the case anymore. Otherwise, we have to fix it. All right, it does not go to the full presentation mode, and now it is, I guess. All right, so welcome everybody. It's a pleasure to be here with you. We have very interesting discussions today, and the speakers you will see. The topic was already announced, and it's related to the life cycle assessment and how life cycle assessment can support innovation in projects that are related to mining and metals, minerals and metals. This webinar is organized in the context of the Horizon Europe project METALLICO. METALLICO is a 4-year project with 13 million euros budget involving 21 partners from all over Europe. I can say a few more words about METALLICO on using the following slide, which is this one. So the core business in METALLICO project is to develop 5 highly innovative processes to recover battery metals from low-grade minerals or residues from industrial activities related to the production mostly of copper, lead, and sulfuric acid. You see that in my slide, the 5 processes with their names and the target battery materials that is supposed to be recovered. The idea of developing these processes is an idea of introducing innovation in a sector that we know is a very large one and sometimes not particularly well known for the reactivity in terms of innovation. Well, actually, the industry, the mining industry and the metal industries are sometimes very conservative. Indeed, there are new processes that are under development, and the idea of using life cycle assessment to support this development is exactly what we are going to discuss today. We will pick 2 of these processes, Cool Plus and TAILCO, the first 2 one, and this will be the content of the next presentation. In METALLICO, I and my team, and you will know 2 of my team members in a few minutes, are taking care of one work package that is dedicated to sustainability assessment tools and how the sustainability assessment tools can be used to support the partners using the tricky process of developing the innovative process and make it work. We know that the life cycle assessment is currently used quite a lot in the mining and metal industries. There is a huge interest because of a number of problems. On top of everything else, we have combat climate change and decarbonization, and therefore life cycle assessment is also used to understand where greenhouse emissions are coming from and in which way this can be somehow understood and decreased through decarbonization strategies. So this one aspect which is certainly of high interest, but this is happening at the full industrial scale, and that was the content of one workshop that took place nearly 1 month ago, mainly organized by University of Missouri and my dear friend and colleague Kwame, who was the moderator and the organizer. There is a substantial difference from that workshop and this one, but there is a continuity. So that workshop was about LCA applied to mining and metals at the industrial scales. Here we are at low TRL, and we have a number of problems that we will discuss with all the speakers from this point on. So we know that life cycle assessment, when applied to a process which is not yet at the commercial scale, is having a lot of problems related to data availability or data gaps or understanding in which way these data and information can be used to understand the environmental performances of the process. We know that on one hand, if we are able to early measure some of the environmental indicators that are bringing useful information, we can pass the information to developers of the technology. And at the beginning of this process, despite the data gaps and the problems with how to conduct LCA can make sense, So if on one end we have these problems for conducting the LCA, on one hand there is still a lot of space and possibilities to intervene and change the way the technology is developed and therefore target better environmental performances. So this is something that will come back in a few minutes. You will see with the other presenters and the way they will show in which aspect there is something to be discussed, to be developed, and in which way this can be useful to introduce innovation in the minerals and metals industries. So this is a kind of an anticipation of two of the bar charts that you will see later on that will show approaches to two of the processes of the project METALLICO, Cool Plus and TAILCO, as I said before, where we will discuss with Stefano and Gyslain in which way life cycle assessment is conducted, what type of results you can have, and in which way these results can be meaningful and can be helpful. This is something which is clearly related to an application of life cycle assessment that undergo the name of prospective LCA, which is what I tried to introduce quite quickly with the previous slide. And here we have to understand what we can do and what is useful and what is really useful. So with this early application of life cycle assessment, we can certainly identify problems or hotspots. We can use scenario analysis to understand in which way the situation could evolve in the future. We can consider a number of alternatives and help the partners in a project like METALLICO or Kikero, which is the other project that we will discuss later on, to understand in which way they can improve what they are doing and understand in which way a possible improvement can maybe somehow entail a trade-off, because maybe sometimes you improve something in one sense and you have a problem in some other sense. So this is the context in which we work, and I'm getting very close to the end of my short introduction. Of course, in the next presentations, we will discuss about availability of the data and the limited data availability, the high uncertainty of data, the certainly big problem, which is the nearly impossibility to understand the real energy use when you are at the low TRL, both at the lab scale or the pilot scale, in which way you could upscale, or this upscale to the commercial level could be purely theoretical or could somehow make sense, in which way you conduct your life cycle assessment, and in your dialogue with the project partners will change 100 times what they are doing and adapt, because the process needs to be fine-tuned in many aspects, and so your data are continuously changing, and this is a problem. And then the proxies that you use, how they can support, if they are good proxies, or in which way you could one day change the proxies with the real data. So that's the end of my short introduction. I more or less kept the time, but not really. I will stop sharing the screen in a few seconds, and this is the agenda for the coming speakers. So I think I will just now introduce the two speakers that will speak about the project METALLICO, and later on we will see the others that are coming and in which way they can bring complementary information to this discussion in view of the Q&A. So without further delaying the next stage, I introduce Stefano Antonini, who will be the first of the speakers to discuss about how life cycle assessment has been used in the project METALLICO, and the discussion will be on the TAILCO process. Thank you, Stefano. The floor is yours.
All right, thanks. I think you should be able to see my screen, right? Okay, so well, thank you so much for the introduction. Now let's actually try to see what it can mean in practice to apply what we defined as prospective life cycle assessment, and taking one of the processes that is being developed within the METALLICO project as a case study. And what I will try to do is try to describe how our support to process developers evolved throughout the project, along with the process itself and the data we had available And the main goal, what I want to do at the end, is to, well, highlight a couple of key takeaways that I think can be extended and generalized, and that will for sure allow to highlight well, the challenges and also the priorities that we should focus on when trying to support process development at these early stages of development. Now, the process I'm talking about is the process that you see right here on this slide. So it's a process that takes liquid effluent that is generated from copper hydrometallurgical processing. And well, currently this liquid effluent is after recirculation sent to a wastewater treatment plant. And the idea, the goal within METALLICO is to develop a process that is able to, first of all, recover the cobalt that is contained in this waste flow, and to recover it in a way that can be used to produce high purity metallic cobalt. But also the goal is to develop a process that is able to maximize the extraction of value from this waste flow. So that means recovering also the zinc, which is another key element in the feed, and sulfuric acid, which can then be internally recirculated within this copper hydrometallurgical circuit. Now, let me just take a brief step back, because I want to highlight briefly how METALLICO is structured, just to give you an idea of, well, what type of data we had and when these were available to us. So the first activities within the project involved mainly the optimization of the processes at lab scale. So this means that for the first year and a half, most of the data we had were, well, results of laboratory tests. So these data then were used to develop some mathematical models of the processes, and the simulations that were conducted helped to define the optimal setup of each pilot plant. So now we are almost at the end of year 3, and well, the construction of the pilots is almost completed, and very soon we will also have the results of the, well, different pilot tests. So we will also integrate this data in our sustainability assessment. Now, what did this mean in practice? So as I said, well, in the first year and a half, most of the data we had were just results of laboratory tests, which means that by that time, at this stage of process development, the type of data that you have is something like concentrations after specific tests, or the efficiency of a process under specific operating conditions, or also the relationship between process efficiencies and a specific operational parameter. So, and this is more or less the type of data that you will have if you want to conduct a life cycle assessment of a process that is only developed at laboratory scale. So what are the challenges here? Well, first of all, especially when the process is not still optimized, you might have a lot of data, a lot of results of different laboratory tests conducted under different conditions, and that they show very different results. And here the challenge is to identify some key parameters that could actually represent the behavior of your process. Now, another big challenge is that, well, ideally, to run your life cycle assessment, you will be able to find some data that allow you to fill this kind of input-output table that you see on the right. The problem is that in many cases, the data that you have are not enough to get to this type of data that you need. And also, they are the results of processes that are conducted in a batch, and you need to be able to interpret them and translate them into a more continuous operation that in many cases can involve recirculation or other, well, things that are completely different than what is done in a batch. And another major challenge is related to the fact that at this stage, you still very often lack any type of indication on the waste and emissions generated and the energy consumed. And well, that is because most of these data are not really helpful when you're trying to optimize a process at lab scale, and they're either not measured, or in most cases, they cannot be measured. So obviously, at this stage, we are in a situation where there's a huge trade-off. So potentially, we could influence significantly the design of the process, but also the possibilities of developing some meaningful assessments are limited because of the limitation of the data. So our approach within METALLICO was to start to support process development even at these early stages, adopting a simpler approach. So one example could be to start to associate specific reagents to environmental impacts, so that we could start to introduce also an environmental perspective within the decision-making process. So for instance, in many cases in Metallico, we were testing different reagents to do the same thing. So, these environmental aspects could help in some way to decide at a certain point which one of these chemicals we want to use for our pilot plant. Now, after this initial stage, the process went to, let's say, a transition phase. So it was optimized at laboratory scale, and it was about to be upscaled to pilot. So within Metallico here, in this stage, the type and amount of data we had changed quite considerably. So now we had a potential mass balance that was obtained through the simulations conducted with the mathematical models of the process that we developed. And also we had initial information on the potential energy consumption of the process based on the equipment that was going to be used in the pilot plant. Now, I want to highlight that this is a very unlikely situation, and that in many cases, still at this stage, you do not have any quantitative information on energy consumption, which is one of the key challenges. And I'm sure that in the next two keynotes, we will see different ways to try to solve this data gap. Now, starting with this data, we were finally able to conduct our first complete life cycle assessment. And the first thing that we had to ask ourselves was to understand what the results we obtained represented. So in this case, the first results we obtained represented the potential operations of the process, the potential environmental impacts of the process when conducted at pilot scale, and if we consider the, let's say, efficiencies that were demonstrated at lab scale. Now, obviously, this is a kind of pessimistic situation, but it's also a very useful scenario because, first of all, it described the current stage of development of the process, and also it allowed us to set a baseline that we could use then to measure how different choices within the optimization of the process could lead to specific environmental benefits. Now, to this end, during the construction of the pilot, what we did was to develop some explorative scenarios with the help of process developers. And the first scenario, one of these scenarios considered, what the industrial partner were expecting to achieve at the end of the project. So after the test at pilot scale. And the other scenario included also some improvements that we expect to see at industrial scales. And this kind of scenario is very useful, specifically regarding energy consumption, because at pilot scale, we are still using equipment that is very, very energy inefficient if compared to industrial equipment. So we need to understand when we are looking at the results of our life cycle assessment of the pilot plant, if the energy consumption is a big hotspot, we need to understand if this is just because we're using very energy inefficient equipment so that at industrial scale, this won't be a problem or not. So this approach allowed us to, derive some useful insights that could be used for within process development. So this is an example. So here we said, okay, let's say that our process followed the evolution trajectory we defined. Probably we will be able to reduce impacts by this much, considering what were the impacts for our baseline scenario. Now, if we want to focus more on specific impacts and we want to reduce them more than this, then we need to start to consider the optimization of different parameters that initially we didn't consider. So we might need to adopt a different approach when optimizing the process at pilot scale. Then another kind of useful insight that we obtained is this one. So what we saw with our first LCA results was that in many cases, the reductant that we use, even though it was used in small quantities in respect to other chemicals, was one of the main hotspots in many cases. And we saw that potentially if we are able effectively to reduce the consumption of this reductant to stoichiometric levels, we can observe notable improvements from an environmental perspective. But also what we saw is that in many cases, in other cases, focusing only on the reduction of this reagent is not enough and won't have a big impact on specific impact categories. So we might need, if we want to prioritize something else, to change our approach, change our key parameters for optimization. And well, I'm sure that at a certain point we will have to accept that we will have some trade-offs, so that some strategies might reduce some impacts, but not others as much as we want. So we will, well, have to decide which way we want to go. Now, just to summarize, I want to highlight a couple of key takeaways that I think can be generalized not only to METALLICO, but to all other processes and projects that are in this kind of situation. So what we've seen is, well, sustainability assessments at this stage of development are highly iterative, and they need to be able to evolve with the process and with the data that you have. And for this, it's essential to have a strong collaboration between all partners involved. And also what we've seen is that in many cases, if we want to support process development immediately, so at the earliest stage of development possible, we need to be aware that in some cases, the data that we have are limited. So it's better to opt for a simpler option rather than waiting for more robust data to come. So, well, I think I can stop here and I can leave the floor to the next speaker. Yes.
Oh, thank you. Thank you so much, Stefano. I think this was a very good job. I'm sure everybody has appreciated. So this is it's clearly a business to business life cycle assessment. And you have shown in which way the team in charge of LCA is trying to interact with the team in charge of developing the technology. So this is the point, and the type of results and the communication and the many things that you have highlighted are precious in my opinion. So I understood that Gyslain is online, so he had troubles like me to find the right link. So he's in my team, so I'm teaching in which way you can mess up when you when you are in a webinar like that one. So if you can show up Gyslain and share your slides, it would be the right time. We are still in METALLICO, so still the same projects. We are changing the technology, and we are going for lithium at this point. Thank you, Gyslain. The floor is yours.
Thank you, Gian Andrea. I hope everyone can see my screen and hear me. So now I will be presenting another process within METALLICO, which is the Cool Plus. And like he has other processes, so the Cool Plus recover lithium battery grade from primary sources. So just a quick outline about the presentation. So the first section will be about some key characterization of the process itself and conventional routes. And in the second section, I will be discuss on the scenario development to support eco-design and inventory modeling. And lastly, we will present some environmental impact range and concluding remark. So jumping in the first section. So some of the main characterization about conventional processes to produce lithium battery grade, they are usually characterized by strong acid, especially in the leaching where sulfuric acid is used, and also high energy input. And the recovery of such process in most of the cases is usually high, above 90%. And the feedstock is usually concentrated before chemical treatment, and the impact range can be around 22 kg CO2 equivalent per product, lithium product. So jumping in the cool plus, so the process is a little bit different from what usually happen during conventional routes, since here for the leaching, supercritical CO2 is used, which help us avoid the use of strong acid. The development started at the TRL4, and now we are transitioning from TRL5 to 7, which is the pilot demonstration. It's currently ongoing. And during the development stage, different ore grade from different sources were used, especially from Spain and Nigeria. And the process itself, here there is a flow sheet of the process, and more about it can be found on the METALLICO website. So primarily we have a pre-treatment, then there is a thermal treatment where the spodumene is mixed with sodium carbonate. Then there is the leaching, which happen due to the CO2 critical. Then there is a concentration stage. Then finally, there is a purification stage where battery-grade lithium carbonate is obtained. So now I will summarize the development which were carried out and how those the input we receive and insight we receive from process developer, and how we use them during our LCA. During the first year, most of the work refer to initial lab tests to optimize the recovery, particularly in the leaching. And during the first year, the information we receive help us to identify a select process flow sheet. Then in the second year, mostly some preliminary mass balance were obtained based on different scenario, and it was also tested on the lab and mini pilot scale. And within the 30 years, so the work mainly consists about finalizing the main process configuration, and currently the pilot commissioning and demonstration is going. So to support eco-design during the development work, we try to build on a scenario based on the process which require a high input of material and energy. So those processes is mostly in the concentration stage and the leaching. So the scenario we built focus mostly around those three stages by trying to evaluate different level of chemical input and energy, as well as lithium recovery. Then, as mentioned previously by Stefano about data limitation and availability at low TRL, so these issues was quite common for almost all the processes. And we had to come up with an approach to construct preliminary LCA. So the approach we use here mostly focus on integrating data from multiple sources, since for some input, so that the data weren't available. So this was particularly the case with energy input. So mainly we use three sources of data to construct the inventory, which primarily were based on direct measurement from process developer, and some estimation also were involved. And finally, we use some proxy. This was particularly the case for energy data, since we had also to upscale some of the data. since they couldn't be used directly in the LCA model. Again, emphasizing about data quality and uncertainty. That can be a big challenge at early stage. So moving on the result section. So the environmental impact were obtained for a different scenario, which had a different level of energy and energy and material. So we try to build the scenario on 2 parameters. Primarily, one was the lithium recovery that could be achieved, and also the chemical recirculation potential that could be achieved. Of course, at a lower TRL, this is usually low, so this is the case, and at a larger scale, this will likely improve. So the key message here is like a different lithium recovery and recirculation can affect the result. And another message here is the scenario which recover the most may not always be the most sustainable. Then when we look on the contribution, so again, we find out like the concentration and the leaching stage contribute to almost 90% of all the impact. So that's why most of the scenario again were focused on these 2 cases. Then when we implement recirculation and we try to project the lithium recovery based on what can be achieved at IRTRL, we found out like some of the scenario in the process can reach global market impact level. And if all the mitigation potential are applied, it can even outperform in some of the cases. And we also try to focus on all the impact category, not only the climate change, because the scenario which perform the best in terms of climate change may not always be the case for other impacts, because they are associated to different elements in the inventory. So like there are some impacts which can be linked mostly to the waste output, some which may link to the material input like the energy and chemical. And furthermore, in the last 6 months, what we have been trying to do is to evaluate the implication of key parameters through the sensitivity analysis by evaluating how some of the process parameters may evolve based on the experiment data. And also we evaluate the implication of the ore grade, which is often a key parameter. Also in the case of METALLICO, because we had a different feedstock with a different ore grade. And some of the key takeaway, one of the main key takeaways is the limitation we observed during early stage. And we had meeting with a partner which help us to refine those limitations and also to close the gap in modeling our inventory, and also the lithium efficiency, and that can be achieved in the recovery, and the ore grade can strongly influence the material and energy input. We have also a key characterization on the mitigation potential, which may depend on the impact category under consideration. And overall, LCA at the early stage was very essential to guide eco design, also to ensure long-term benefit. In the next stage of the development, the first key step will be to refine energy input. in particular, since most of the energy we use at a lower TRL were particularly based on estimation or proxies. Then also the development plan to integrate a waste valorization unit, which will produce geopolymer. And finally, we are planning to refine the scenario we developed based on the level of data quality we will have in the next stage. So that will be all, and thank you for your attention.
Thank you so much, Gyslain. This was also a very meaningful contribution, in my opinion. Again, you gave quite nice overview on the type of work that is currently being done in the project Metallico and how you are supporting the technological partners in their work. So you touched similarly to Stefano, a number of elements that are certainly to be highlighted in a webinar like this. So thank you so much. Surprisingly, we are keeping the time quite well. We now move out from the project Metallico, and we will go back most probably during Q&A. This is a clustering event, and so I can invite the next speaker. It's a pleasure to welcome Aina Masfond from BRGM, the French Geological Survey. Thank you so much, Aina, for having accepted to deliver your talk on another very relevant, very important Horizon funded project. I want to thank you twice because, you know, me and Stefano and Gyslain and Ramona and Diana, we are in the project Metallico. So for us, it's our job to be here, but you are coming for free, and this is very appreciated. On the other hand, we know that one of the goals of Horizon funded projects is clustering, and we take it very seriously. Not only we take prospective LCA seriously and we provide support to the partners, but we also take clustering seriously. And so it's, as I say, it's an honor for us, and we are very interested in listening to your contribution. So if you want to share your screen.
Yeah, sure. So thank you for having me. Very happy to be here. So you hear me well?
Yes.
Great. So, do you see my screen?
Oh, yes.
It's in presentation mode?
Exactly. Perfect.
Perfect. So, good afternoon, everyone. My name is Aina Masfons, and I'm a research engineer at BRGM, the French Geological Survey. And today I'm very happy to be here to present to you part of the work that we are currently carrying out within the Kikero project. So, well, we have all heard of lithium-ion batteries. They power our phones, they might power our cars, and they are considered central to the energy transition. To build these batteries, we need raw materials like graphite, nickel, or lithium, among others. But how much of these materials do we actually need? So there is different scenarios being considered for that, but on the current policy path, so without assuming that every government hits its targets, the International Energy Agency has estimated the demand for graphite, nickel, and lithium to be about 4 times higher in 2030 respect to 2023, or 6 times higher if we want to reach these net zero emissions by 2050. And where will all these materials come from? So one day, thanks to the efforts of many, batteries might be produced largely from recycled materials. Yet today, with the rising demand and the current recycling rates, The reality is that we are still heavily reliant on primary materials and therefore extraction. Often, when we discuss the current energy transition, we refer to it as a clean energy transition, one where sustainability, especially environmental sustainability, is at the forefront. However, it's important to acknowledge that the transition itself, while necessary, is not without its own environmental impacts. So, for example, the production of batteries and the material needed for these batteries carry environmental costs, as we see in this webinar today. So the supply chain of lithium-ion batteries has its own set of environmental challenges. Therefore, to avoid jumping out of a frying pan and into a fire, or simply to avoid burden shifting, it is essential that we assess this environmental impact of the lithium-ion battery supply chain and we consider its influencing factors. To do this, we can rely on life cycle assessment, or LCA, as it is a well-established method for evaluating the potential environmental impacts of products and processes across their entire life cycle, as we have seen already in the previous presentations. And notably, the European Parliament has adopted LCA as the standard method for evaluating the environmental sustainability of lithium-ion batteries, including the production of its key materials. So the presentation today will focus on one of these key materials. But before I proceed, let's quickly recap on the basics of lithium-ion batteries. So a lithium-ion battery cell consists of 4 main components. There is a cathode, the anode, the separator, and the electrolyte. I have briefly mentioned some of the materials used in these components. So for example, there is graphite in the anode and nickel and lithium in the cathode. So in today's presentation, I will focus specifically on one of these key cathode materials, from which nickel sulfate serves as the primary precursor. So in the case studies I will present, I will explore the primary production of this battery-grade material. And at this point of the presentation, let me mention the Kikera project, which is an European project that applies the 12 principles of circular hydrometallurgy to design a circular hydrometallurgical flowsheet for producing NMC cathode materials. It is supported by a strong consortium of 11 partners from across Europe, each bringing its complementary expertise. At BRGM, we are involved in different tasks, including the development of a life cycle assessment within the project. And today, in this presentation, I will present part of the work that we are currently carrying out in this context. So let's start with one of the case studies that we are considering, and let's go with the goal and scope of this case study. So the functional unit was defined as the production of 1 kilogram of battery-grade nickel sulfate. Nickel is mainly extracted from 2 primary types of deposits. So there is the sulfide and lateritic ores. The focus of this case study lies on laterite resources. One of the major producers of nickel from lateritic resources currently is Indonesia, which has become a central hub for the mining activity, and it's the location that we are considering in our case study. The production process for nickel sulfate from lateritic ores involves 2 main steps. So first, there is the production of a mixed hydroxide precipitate, or MHP cake. And second, there is the conversion of this cake into nickel sulfate. This first refining step, we are considering it takes place in Indonesia, with this primary technology used for it, which is high pressure acid leaching, or HPAL. The conversion to nickel sulfate, we are assuming that it takes place in China, utilizing a selective acid leaching process. However, when we apply LCA, as others have mentioned, we have our own challenges. And one of these key challenges comes during the second phase, which is the life cycle inventory phase, when we need reliable and comprehensive data. So there is several strategies for collecting and gathering or generating LCI data. 3 of the most common ones could be primary data collection, data from digital databases, or literature data. So primary data, in this case, for this presentation, involves gathering data directly from production facilities, so providing site-specific, potentially highly accurate information. Digital databases offer another important resource. There is multiple databases available, each differing in the coverage and in the cost. And then there is scientific literature that serves also as a valuable source of LCI data, offering both LCI data and scientific data that can potentially be converted into usable LCI information. So primary data is considered highly valuable, and I would say is the preferred strategy overall. And it's often seen as offering the highest accuracy. Then there is the LCI databases like EcoInvent that generally are essential for background information, but may lack detail for specific foreground systems. And for literature data, it's important to note that a lot of times many studies tend to cite each other without contributing to new information. So this means that a lot of times a large number of references doesn't always translate into a rich source of original inventory data. Then for accessibility, so primary data is valuable, but it's difficult to collect. A lot of times we cannot just call companies and ask, can you please send us information? And a lot of times there is confidentiality concerns, which often, if possible, require lengthy non-disclosure agreements negotiations. For LCI databases, while some require payment, LCA practitioners usually have access to one or multiple databases. And literature data is generally accessible, although some sources may require payment or subscription. For reproduction or further use, the confidentiality issues related to collecting primary data can also lead to less reproducible results. So this data a lot of times is presented in an aggregated or only shared in a summary form. The LCI databases are straightforward to use and come a lot of times with comprehensive documentation, which is helpful for guidance. And then for literature, the way the data is presented can be highly inconsistent. So this inconsistency poses challenges sometimes for data collection and can increase the time required to compile and interpret it effectively. Then for future-oriented LCAs, so primary data only reflects in general the current operations and cannot fully account on its own for future changes or developments. Similarly, no current database fully accounts for prospective changes on its own. However, there is ongoing efforts on exploring how current databases can serve as the foundation for constructing future scenarios. And then literature data, while it might include future scenarios, it's typically tailored to a specific context of the original study, and it's not easy to be modified or extrapolated to fit different future conditions. So these are three strategies that offer advantages. They also have shortcomings, one of which can be this limited applicability to future-oriented LCAs. But they are not the only strategies. So for example, a fourth one that we can build upon and that can potentially help us when we find ourselves at these lower TRLs would be the calculation and or simulation for data collection and generation. So this strategy includes a range of methods that go from simple molecular structure models and stoichiometric calculations to more advanced techniques like process design calculation and process simulation. So as the title of the presentation gives away, in the case study today, we are using process simulation to obtain inventory data. So in this case study, we are using process simulation to obtain inventory data, but how do we do this? How do we accomplish it? So first, a flow sheet or flow sheets are created, outlining all the individual process steps that we need to simulate. For each process step, within each flow sheet, a set of variables, such as process inputs, chemical reactions, and operational parameters, like pH, temperature, type of equipment, all this is defined. This data can potentially be gathered from various sources, which include technical and technical reports and scientific literature, lab scale data, pilot scale data, or industrial data to ensure an accurate representation of the process conditions. For this first case study, we mainly used industrial scale data. So this data is then input into a process simulation software. There are several options available in the market, but for this work, we used HSC chemistry because it's used widely in the mineral and metallurgical industries. One or multiple models can be created for each initial flow sheet, and these models are used for mass balance, optimization, scaling up, and simulation of different ore grades, different inputs, and the technologies of choice. So from these models, the foreground LCI data is extracted, while an LCI database, in this case we used EcoInvent, it's used for all the background processes. Now, if we move towards the life cycle impact assessment of our case study, so we know that LCA can provide a broad overview of potential environmental impacts that range from air and water pollution, including ecotoxicity and eutrophication, to resource use. But today I will focus mainly on these 4 impact categories. So here we have the contribution results from the different units that we modeled. And when we see these results, what we need to keep in mind is first that they are preliminary. So we are still in the process of validating our simulation model. However, the first thing that we see is that the HPAL model in blue is the main contributor to most of the impact categories, mainly due to its high demand of energy and of sulfuric acid. But as I previously mentioned, HPAL is an established technology for the production of nickel sulfate. But today we are in this webinar talking about like lower TRL technologies, so more emerging technologies. And as part of our work, we are comparing this HPAL to a less established technology that is bioleaching. So for this comparison, we have established the functional unit of the production of 1 kilogram of nickel sulfate within the pregnant leach solution, or PLS. And we are considering Indonesia as the location for both technologies. So for the LCI, we have used the same methodology. So in this case, we are considering this mineral concentrate that goes into the HPAL or the bioleaching process to produce this PLS. For the same process simulation method is used, and in this case of the bioleaching, we are using pilot scale data as the main input data for its process model. So for the life cycle impact assessment today, we are focusing on the same impact categories as before. So here we have the preliminary results for both the bioleaching in green and the HPAL unit in yellow. So we can see that the potential environmental impact of HPAL is higher in most of the impact categories, except for freshwater ecotoxicity. This is because in our current model for bioleaching, the leaching residue is considered as an emission to water. So we are currently not taking into account any waste treatment for it. But this is one of the things that we want to include in our process simulation model and put in place, but it's part of our next steps. So what are our next steps? So first, we want to finish validating and verifying this full HPAL route all the way to nickel sulfate so we can lock the final results. Second, we want to adapt and validate the remaining units for the bioleaching route so we can also reach this nickel sulfate, battery-grade nickel sulfate via this pathway. And third, we want to test different bioleaching yields and identify a potential minimal yield needed for bioleaching to keep this potential environmental advantage over HPAL. Then we want to update the LCA results, pinpoint the hotspots, and propose eco-design strategies to reduce all these potential environmental impacts. But what can we already conclude? So in our comparison of HPAL versus bioleaching for nickel production, so bioleaching shows a potential environmental advantage. So this suggests that these emerging technologies can deliver improvements, and it's valuable to assess them early on so we can bake them in this eco-design from the start. A quick note on the process simulation used for LCI data. So in this case, process simulation has been useful. It has given detailed and transparent data, for example, including flow composition step by step, that it's handy for discussing waste streams or dissipation. It has also enforced mass and energy balances, which help uncover optimization opportunities like heat recovery or internal recycling of specific flows. And it has let us explore future variables, so upscaling new technologies, but we can also use it for other things. So it can be well suited for future-oriented LCAs, but of course, it has its limitations. So we see that it has required both expertise in process simulation and LCA. It can be very time-consuming to build very detailed models, especially if there is no prior process knowledge, and also the fact that simulation often assumes ideal conditions. However, we have seen that we can mitigate this by calibrating models to real consumption data and actual equipment performance. So thank you very much for your attention.
Thank you so much, Aina. Very interesting talk, including the introduction, also to explain why we do these type of things. I'm quite sure that also in the audience we have LCA practitioners, and they are experiencing problems like the one we are showing with the lack of data, meaningfulness of the data, mixing data of different types. In principle, we have a first lot of Q&A, so nearly 10 minutes in theory, which are now more 6 minutes. So if there are, honestly speaking, I don't see any questions in the chat. Am I wrong, Ramona? Do you see any? Or
there's no direct question.
We give priority, so I encourage questions if there are. Otherwise, meanwhile, I can start asking, because I have seen a lot of common ground. If I take the two presentations from Stefano and Gyslain, and this one from Aina. So certainly you helped us, Aina, to understand in which way process simulation can be beneficial. We also have used process simulation in METALLICO, not directly because we have an entire work package on that, which includes also that type of activity. So the question could be in which way information from lab, pilot, process simulation is mixed, and in which way the process of substituting better information with the previous one in the models is done. If any of the three of you want to pick up my question, I think it could be of interest. There are many other aspects I'm sure that we want to talk about. Stefano, for instance, oh, Aina, sorry, I stopped you. So please go.
No, please, Stefano, go.
No, I was just asking if I was allowed to make a question to a speaker, but like, I can wait. I know if you want to go, please.
So I was going to say that probably in our case, we are always trying to improve the models, the process simulation models, while we get new data from the lab, from the pilot. It's tricky sometimes to mix data from different sources, and what we try to do is to always validate and verify the assumptions that we are making, either by asking experts within BRGM or within the project, and also always being very transparent with what we are using behind our models. So we do build a whole documentation around that we want to share with the model, to be transparent how any LCI data that we use after is calculated.
Yeah. I'm afraid also the second question is for you, Aina, because we have a question from the chat from Jose Luis Cortina. Hi, Jose Luis. He's a dear friend and colleague in the project METALLICO. The question makes sense to me, and the question is, how relevant in LCA is the location of the study?
Well, I would say in general, in LCA, the location can be quite relevant, especially, for example, for the energy production or that you consider. In our case, we considered Indonesia because it's one of the current main producers, global producers of nickel in the world. I don't remember the exact, but it produces more than 50% of the nickel worldwide, and we know that the mining and this first step of refining is done there. And we also know that the electricity mix of Indonesia is highly reliant on coal. So definitely this has an impact in our results. It would be different if we were considering the electricity mix of France.
Again, thanks. Before we move on, I also want to to re-emphasize something I said before, because based on the discussion so far, I say that minerals and metal industries are known not to be innovative industries. So it seems that I was very wrong in what I said. So there are a lot of ideas and new ideas, and many technologies are under development. Maybe the statement about the lack of innovation is related to the fact that some of these technologies needs a long time before they are effective. But the last speaker will be from industry, so I was afraid that Andrea would have been upset with what I have said, but I corrected myself in this sense, because until what we are doing will not show to work, it will not be adopted by the industry, and I mean the industry can only adopt what is really working. So the goal of what we are trying to do is to assist in this process and make it happen faster, because we don't have much time, and possibly have let's say lower environmental impacts if we can. Let me ask a question to Gyslain, because he was the only one who could not speak, because also Gyslain, like Aina, started with benchmark information. How much are the environmental impacts related? Also, Stefano did something very similar. Are the environmental impacts associated to conventional lithium and best results from the LCA that you could find in the literature, which we know is something which is evolving. This was also mentioned in some of my in some of my slides. What's the problem with that? Do you think these benchmarks are so important? Do you use them to talk with the partners? Are you scared or are you upset when you see that some of the impacts related to some of the processes or reagents or energy use or whatever are showing very high impact at that stage? So what's your reaction? What's your point on that?
So the first approach we use, of course, was to identify the benchmark, not to initiate a direct comparison with those processes, because we have to consider the TRL. So those processes are already at the TRL of 9, and we are still at early TRL. So this is a key consideration. So the benchmark are mostly used to identify and understand which process stage contribute the most, because at the early stage, this is more important than having a single value of the impact. So it's much better to understand the range and how it can evolve with the development. So that's why in the last stage of our work, we try to understand the implication of key parameter. So some of those key parameter can be associated to the feedstock, which is the ore and the ore grade, and some of those can be also associated to the efficiency which can be achieved. So this is those parameter. They can dictate at some extent the energy and the material input of that process. So just to sum up, so the identification of benchmark was very useful for us, since it gave us some insight on how the process may evolve in time and what should be improved.
Indeed. So this was very important to highlight, Gyslain. Thank you so much. So let's move to the second part, which is something more related to higher TRL, or how the industry perspective can tell us whether what we are doing makes sense or not. Before I give the floor to a friend and colleague, Professor Luca Ciacci from University of Bologna, let me still highlight one point, because in my short introduction, I say that LCA is currently used a lot in the minerals and metal industries. There are guidelines, there are new life cycle assessment published by big producers. So some you have seen in my slide. We behave like if at the industrial level, at commercial level, life cycle assessment is something well known, fully developed, with the perfect guidelines and perfect guidance and perfect data. But this is not the case. So this is something that is still under development. So when we are at low TRL, we just have more problems. But still, some of these problems are something that in many we are trying to fix worldwide. And that's why we invited Luca Ciacci to talk about an application of life cycle assessment at the industrial level, but where some of the, let's say, most known and still unresolved methodological problems are still there. So the discussions from the speech from Luca will be about recovery of multi-metals from waste, which is something similar to what Stefano has tried to describe about METALLICO, but at lower TRL. But still, I'm sure that in the discussion with Luca, we'll see something very interesting at food scale. Thank you, Luca. Floor is yours.
Thank you, Gian Andrea, for introduction, and I wish also to thank the organizer for inviting me to contribute to this webinar. Let me show my screen. I would ask if you can confirmation if you can see in full.
Not yet full screen, but still low TRL presentation. No.
Okay. Is it now?
It's quite the same. We can see perfectly, so that would not be a main issue, I would say. But still, it's not in full presentation mode.
So it's the presenter viewer or
not yet?
Not yet. Sorry, you can't see the full
we
screen.
can see the slide quite large, but it's not. I mean, it's not that you swap the two screens or the three screens that you have, because it still shows as in the normal mode, not the presentation mode.
Okay, so let me check what's wrong. Apologize for this technical.
Yeah, maybe you reshare.
Can you see it now?
Okay. Yeah, perfectly. Full screen mode.
Does it
now.
work? Does it work?
Yeah.
Okay.
Go.
Thank you again, and apologies for this technical issue. So as I was saying, thank you so much for inviting me to join, to contribute to this webinar, and possibly provide some insights from our recent work on life cycle assessment applied to precious metals recovery. The idea is to give some highlights on how challenges with data and uncertainty may also affect, as you mentioned, Gian Andrea, full-scale industrial applications. So going straight to the point, we applied LCA to an integrated refining plant for precious metals recovery. This plant is located in Tuscany, Italy, and it's owned by TCA, which stands for, it's the acronym, the Italian acronym for standing for Trattamenti Ceneri Auro-Argentifere. The system in LCA terms, we could say, provides multiple functions, because as you can see, we have different waste inflows treated in the plant, including manufacturing metal scrap, spent catalyst, liquid waste, and incineration ash. On the other side, we also have different co-products delivered by the system, namely silver, gold, palladium, platinum, and rhodium produced as single metal ingots out of the plant. We believe that part of the novelty, the value added to this study is the fact that most of the existing literature on precious metals recovery typically applies LCA to single waste streams, mainly e-waste or printed circuit boards in many cases. And precious metals are recovered together with other, let's say, base metals in this context. While here we have a facility, a refining plant entirely dedicated to the recovery of silver, gold, and the PGMs. As you can see, the usage stage of single individual metal ingots, as well as the end-of-life stages are excluded from the scope. These assumptions also align with the product category rules, PCRs, for basic chemicals, and also because, as you can understand, precious metals are intended to remain essentially indefinitely in our society to some extent. Yes. So let's take a look at the system definition and the main key elements in our model. We look at 1 year coverage with data collection. It was the year 2022. in which 127,800 kilograms of precious metals were recovered, produced. We selected as the functional unit 1 kilogram of precious metals, recovered for 1 kilogram for each of the 5 selected targeted metals, with the purity of 99.95%. That grade is a kind of a minimum threshold level reached for all the 5 metals. For some of them, the company is also able to provide much higher purity, much higher quality grade. We applied a zero burden approach to the waste inputs, which is, as you may know, incoming waste does not hold the environmental impacts for its generation, but only, let's say, for treatment at end of life. We apply the environmental footprint 3.1 method and cumulative energy demand as LCA methods in the assessment. The system is quite complex network of processes involved. We see here I would say simplified, very simplified flow sheet, where essentially we have the incoming solid waste and residues from the manufacturing, metal manufacturing industries, undergoing a first thermal treatment, incineration, to produce ashes rich in the precious metals. Then these ashes are sent to the smelting unit for undergoing a second thermal treatment at higher temperature, out of which we get a mixed precious metals streams sent to further refining. The outflow from refining are the individual precious metals ingots. Out of smelting, we have also some liquid residues, liquid waste, which are collected together with the refining liquid residues and supplemented with the incoming liquid waste to the plant. The liquids treatment unit then separates, has a solid to liquid separation stage, so that sludges can send either to the incineration or directly to smelting, depending on the composition and the concentration of the metals for further treatment. As I mentioned, this is a very simplified flow sheet. As you can expect, reality is much more complex. Here we see I would say a partial snapshot of the real scheme, of the real process, in which there are many recirculating flows for the different steps, different stages for processes. You know, precious metals have relatively high market value, so that it's a strong incentive to maximize their recovery to the level possible. And that's exactly what happens in the company. So essentially, they want to recover all possible gold, silver, and the PGMs containing in the incoming waste. And this may be a fundamental limit to data collection, to data gathering, because in this plant, at least, it was not possible to reach the desired level of granularity for data collection and information gathering, in the sense that although the company, of course, knows very well the list of material inputs and all the outputs, including energy and material streams, still it may be challenging to model exactly all the mass and energy balances for all the steps we have in the system. In principle, this is doable. We could also apply, as previously suggested, process calculations, or we could also call, we are actually in the situation to call directly the companies. Still, it's always balancing of the resources needed for making reliable model, but simplify enough to be representative of the real situation. So that's always a balance and evaluation we have to make when we create models which are simulation, an estimation of the real world, let's say. That said, we were so in a situation where it was not possible to create unit processes in LCA terms for each of the stages covered in the system. And in this case, as you know, the ISO standard suggests as possible hierarchy of solutions, starting with the subdivision in sub-processes. This was not feasible. The system expansion may not be the best option in this case, so in the end, allocation was likely the most handleable approach to solve multifunctionality issues. It's worth reminding, I guess, that allocation is an artifact, is a mathematical artifact. So we try to solve issues, but being aware that this doesn't necessarily reflect real world processes. So we always have to keep in mind that these artifacts may not exactly be the real world process we are modeling. On the other side, allocation somehow is comforting because we can always make consistency check. In the end, the allocation factors sum up to 100% of the impact. So in this sense, we are not excluding, we are not neglecting possible impacts associated with the system. And coming to the criteria applicable to allocation, we considered either mass and economic criteria. In the end, revenue generation is the driving force behind any industrial operations. So that's why we also considered economic allocation. But following the general guideline, the general suggestion from the LCA community to look at an average time horizon of at least 10 years to avoid possible spikes and drops in the market value of metals. Here we see the example of silver for the last 10 years. And remember that our time horizon look at 2022, so we look at the past 10 years, where its market price was relatively stable, flattening somehow, while in the most recent years, essentially a few months ago, silver experienced a quite increase in its market value. This is even more relevant for rhodium, which exactly around the year of our reference, our temporal horizon, experienced really high spike in its market price. And this, of course, may have some consequences on the allocation factor derived on economic criteria. Of course, averaging the market price over 10 years somehow buffer this effect, but still it's something which may affect the creation, the artifact of having allocation factors based on economic consideration. Here we see, in the end, what are the mass allocation factors versus the economic allocation factors. So if we look at the mass ratio, most of the impacts on a relative basis are associated to silver because it's the metal recovered in the largest amount, followed by gold. While if we look at the economic ratio, gold is the most contributing, let's say, metal, as either combination of relatively high amount recovered and relatively high 10-year average market price. We also, of course, we went through different issues with data collection. We collected primary data as much as possible using checklists, usually in Excel format, and that was they were compiled by also with the support of the owner of the plant. This data included in particular information related to the raw materials used, the auxiliaries, energy consumption, and air emissions for the reference year. There were more than 140 material inflows to be univocally identified and quantified, and 16 waste types according to the European waste list codes, outflows to be disposed or sent to final treatment, which were included in the model. Of course, we had to go through several consistency checks to verify, validate our assumptions, including also cut off to certain flows when their exact composition was unknown or not clearly quantifiable. For instance, we had a row in the checklist saying crucibles, but it was not clear for how long these crucibles are used in the plant, and so we decided to exclude them. Also, being aware that in general, most of the flows excluded were much below 1% on a mass basis. I think one interesting issue relate to the air emission monitoring. The plant, of course, is required by legislation, by national legislation, to monitor substances released to the environment, which include a quite comprehensive, I would say, list of pollutants. The point is that carbon dioxide, based on national legislation, is not required to be monitored. So as they had no idea of how much carbon dioxide could be released from their plant, which is of course quite relevant, especially for global warming considerations. So we had to approach this by applying calculations, estimations, and we model the carbon dioxide emissions as a function of the different fuels used in the system, namely propane gas and natural gas, based on the stoichiometry and the combustion efficiency, where the net carbon converted to carbon dioxide resulted from the difference of the total carbon theoretically measured from the inflow of propane and natural gas, subtracting the amount of carbon that was likely released as carbon monoxide, so kind of a partial oxidation in the combustion reaction. Secondary data, I will go relatively quick across them because they were already touched by some of the previous speakers. So background data mainly relied on EcoInvent databases. We refer to average European market processes or the global averages. The energy consumption for electricity was based on company energy bills and model according to the national electricity grid mix in Italy. For raw materials incoming to the system, to the plant, transportation referred to average distances reported in the EcoInvent database, although we had the information about the real distances covered by waste suppliers and raw materials supplier. Now, the idea of using average market distances based on EcoInvent was motivated by having more reliable, more robust, I would say, data, and in this way buffer possible changes switching in the supply chain of the different materials. However, we used the real distances covered for sensitivity analysis. Finally, there was also some internal transportation of waste and materials, but unfortunately there was not emission monitoring for heavy transportation. So also in this case, we had to estimate possible emissions. We knew which type of heavy transportation means were used, and based on the environmental declaration published by the producer, we could also calculate the theoretical emissions for certain substances that occur in an average year, because the company had only monitored three periodical monitoring for the working hours, but no information about the consumption nor emissions. So that was one approach to solve this lack of data for collection. Data quality, uncertainty. So we evaluate the uncertainty by applying Monte Carlo simulation for uncertainty propagation. We considered 1,000 runs. Primary data were shown to be relatively sure. For air emissions, since they were based on different periodical monitoring, we considered a triangular distribution, which is typically suggested for air emission monitoring. Secondary data, uncertainty ranges are reported in the EcoInvent database. We applied the pedigree data quality metrics when only one single value was available. And of course, we included also the standard deviations for the metals market price, as mentioned, used for the economic allocation. Sensitivity analysis covered the top 7 material flows by mass. And based on these top 7 material flows, we played with the distances as mentioned. So by switching from the average market distances reported in EcoInvent versus those actually covered for the supply chain. And anticipating some of the results, the sensitivity analysis results were much lower than the uncertainty analysis results. So in this sense, we could say the model is relatively robust. Here we see some pictures of the results in terms of contribution process, where mainly chemicals, energy carriers, and gases used in the system contribute to the majority of the environmental impacts. This is, in the end, the core business of the company. They want to recover precious metals from waste by applying chemical processing and energy in the end. If we look at the elemental flows, so process contribution, nitric acid and sodium hydroxide are definitely relevant to some of the impact categories. We have also electricity, which is depicted in red color and contribute and spread out almost all categories. And also refractory materials, which means mainly alumina, also contributing to some of the impact categories. Here we see just a comparison of the carbon footprint results as dictated by the different allocation criteria. So on the mass carbon footprint, we see that essentially we are averaging the carbon footprint among all the metals, while when you apply economic allocation, we can appreciate differences as based on the market values. We also compare the carbon footprint results with the existing literature relevant to precious metals recovery. And in particular, we refer to one publication by Phil Nuss and Matt Eckelman, Life Cycle Assessment of Metals. They also applied economic allocation. So for us, it was interesting to compare the results, even if the comparison is not comparative, sorry for the same word, in nature, but rather they are intended to provide a sectoral benchmark for results discussion against a global reference context. The blue bar represents gold, the carbon footprint of gold and silver production from virgin ores and mines, while in orange we see the contribution of secondary production, with the zoom in on the right-hand side panel for better understanding. So our results are the bars on the right-hand side, while the estimates from Phil and Matt on the left-hand side. As you can see, they are comparable in nature. Of course, they have different uncertainty ranges, which comes also to the need of being accurate and precise to the system under investigation versus more global averages, which have higher variability. The same can be also seen for the PGMs. Also in this case, primary production is definitely much higher compared to secondary production. For palladium, we got similar results, a bit lower for platinum, relatively lower for platinum, and similar also for rhodium. going to the conclusions of wrapping up on what we have seen, I hope that this was somehow illustrative for issues, challenges with data gathering, data collection, and information availability, also at full-scale industrial application, where in many cases we have the information already somehow optimized for the real operating conditions, but in some cases we might not have the enough granularity, enough scope level to create detailed LCA models. And this may be a limiting factor for companies, for industry, because it somehow prevents the possibility of pointing the environmental hotspot, so where most of the environmental impacts are located, are locked in, and so support possible improvements in the in normal operating conditions. Allocation is an artifact, as I mentioned. It allows consistency checks, so in the end we can include all the impacts, but still it might be debatable whether it is representative or not for the real situation. That's also why in LCA it's worth reminding that we should talk about potential and not actual impacts. I would also mention that although the comparison, the sectoral benchmarking is promising, is comforting, it's also true that we should avoid, or we should carefully check our results and avoid possibly to make universal generalization. We always want to have univocal, unique, clear preference, order of preference, but we should always be aware that our results, our LCA results are really context dependent. And so if we change parameters, if we change variables in our system, we should also expect that our results may be different. The study underwent an external critical review, and additional information are reported in our paper. You can see here the main references, and I think that this is it from my side. Thank you so much for your attention.
Thank you so much. Thank you so much, Luca. Indeed, as I said, this would have been very meaningful, and it was. As you have highlighted, there are still a number of open issues from the methodological point of view, starting from the zero burden assumption when you deal with a waste, which might be the case also for some of the processes of Metallico. The allocation and many other things are quite meaningful and should be considered. And when you are at low TRL, this is becoming really challenging. So it's time. There is already a question for you in the chat, but it will go to the end because we have foreseen a final wrap up if we still have time. So now it's time for Andrea Di Masi. We waited long for you, and you waited long for us. Thank you so much. Andrea, he is representing SQM. SQM is a major producer of lithium, operating in several countries. So you are a big one representing the lithium industry. So I'm sure you have questions on the Cool Plus process, but I think you have also many other things to tell us. And so let us know the industry perspective in this context. What you think about. Floor is yours. We already see your full presentation mode, so please go ahead.
Perfect. Thanks a lot, Professor, for the invitation. So I will try to contextualize LCAs in the wider environmental and sustainability strategy and action of SQM. So before starting, a customary note regarding forward-looking statements. So this presentation will include statements which are based on the best assumptions known as of today by the company. And going into the presentation, I will give an overview of SQM, then share our approach regarding transparency, LCAs, and then tell you a bit more about what innovations we are looking into and what kind of environmental assessments we are making in relation to the innovations that we are considering our processes. So SQM is chemical and mining company with the core of operations in the north of Chile. In this slide, you can see the key divisions of the company. I represent the lithium division, and I work in the external affairs team. So you will appreciate if my presentation is not as technical as the previous one, but I still hope to give you some insights on our thinking. So in this slide, you see the production process in our operations in Salar de Atacama. So we are an integrated company. We extract lithium from brines. So the process consists in the evaporation in the brine concentration process, for which we obtain lithium chloride, which contains around 6% of lithium content, which is then sent to our plant in Antofagasta, which is around 200 kilometers from our operations in Salar de Atacama, in which we produce both lithium carbonate and lithium hydroxide, according to the process that you can see in this slide. At the moment, the refinery in Antofagasta is the biggest refinery operating globally. We have increased our production to indeed meet the customer requests and the market demands. And we, as I said before, are able to produce both carbonate and hydroxide. So depending on what the battery chemistry is. And we strive to produce with the highest quality to meet the qualification needed by our customers. And with this comes responsibility to produce in the most sustainable way possible. And since it's not possible to manage what is not measured, of course, we need to closely monitor our processes and measure the impact and the footprint of our operations. And that's where life cycle assessment comes also into play. Before going into LCAs, let me give you an overview of our actions and targets when it comes to driving sustainability and reducing our footprint. Here you see our targets when it comes to the reduction of brine and reduction of continental water. Later on, I will show you also the reductions that we have already achieved in the past years. And we also have partnered since the launch of our sustainability strategy in 2020 with different initiatives, which you can see also on the slide to validate our approach. And one of the key ones is IRMA. I don't know if you have already heard of it. Is an initiative for responsible mining assurance. It's a voluntary sustainability standards which gathers all the stakeholders involved in mining operations, including local communities, indigenous groups, companies, finance sector, and the public institutions. And it has 4 pillars. And one of them is, of course, environmental responsibility, which is actually the one in which we scored the highest in our evaluation. So transparency plays a key role in our approach. So in this slide, you can see the different monitoring points in our operations, both for the brine wells, but also for the industrial water wells. And also you have a website which is called SQM SN Linea, which provides to stakeholders publicly all the information related to our extraction levels of water, brine, but also other environmental parameters, for instance, related to biodiversity. And as I was mentioning before, we have already achieved substantial reductions when it comes to the brine and water extraction, leading to de facto also a reduction in the intensity, the footprint in our operation. So in the graph, you can see the reduction in the water intensity and the increase of production at the same time. And then going into the LCAs, so they're a crucial tool to understand better where we can further improve and reduce our footprint. So when it comes, for instance, to the carbon footprint, we can see that our process is already in a good place, and according to benchmark minerals, we are at the lowest level as a company when it comes to the carbon emissions for lithium production. And this level has concrete impact also when we look at the overall footprint of battery cell. So in 2021, we contributed to study done by the Argonne National Laboratory using our data and adopting LCA methodology to compare the footprint of lithium from brine and from spodumene ore, and in the different bars in this graph, you can see how this at the end impact the footprint of two types of cells, one using lithium from brine, lithium carbonate for brine, and one lithium hydroxide from spodumene ore. And regarding our current approach related to LCA, we deliver cradle to gate carbon footprint information for our products to also help customers define their emissions and continue improvement, and provide for the greater transparency of the battery value chain. So you can find more information also about our LCA approach in our sustainability report, which was recently published. And in 2024, we performed two LCAs actually, an environmental LCA and also a social LCA, which I will tell you more in the next slide. So our LCAs have been also in the past critically assessed by third parties, and we of course value a lot this approach to provide more transparency and to bring improvements in our operations and in the adoption of the new technologies. Something that I think it could be interesting is a recent social LCA that we have performed in collaboration, which was performed actually by TU Berlin, which looks at the impacts, especially on water and the local community. Because from our point of view, of course, LCA, environmental LCA, are very important, but needs to be also contextualized in the area where we operate. And we operate in Salar de Atacama, which, as you may know, is a arid area in the north of Chile, and whereby the water, it's something, of course, very important for the local communities, not only for their well-being, but also for their cosmovision. So when we adopt new technologies, we don't only need to look at the carbon footprint, for instance, or the other parameters, but also at the priorities and the concerns of the local communities. So to apply the best solution according to the context where we operate. So it's not only a technical assessment, but has to consider the local situation. And also that's why we decided to go for this social LCA, which according to the authors of TU Berlin is the first done in the lithium industry. And then when it comes to the next steps and also the new technologies, which also is probably more interesting for this webinar, we are looking at new solutions to improve our operations, both in terms of lithium recovery, but also in terms of reduction of footprint, brine reduction, the reduction also of the ponds, and reduction of industrial water. So we are looking at different technologies, and we will apply a combination of them. So the three types of technologies we are evaluating fall into the categories of membrane filtration, mechanical evaporation, which by the way is already used in our refinery Antofagasta, and thanks to this process we already cover 47% of our water needs in the refinery. And then DLE technologies. We have already explored and evaluated more than 140 technologies and performed a dozen of field tests with our brines in Salar Atacama. And as linking to what I was saying before, these new technologies, which goes under the innovation roadmap called Salar Futuro, are always assessed and evaluated according to the local context. So we have already consulted different types of stakeholders, from local communities, farmers, university, tourist guide, press, and trade unions, to also hear their perspective on the technologies that we are planning to apply. And next year we will submit an environmental impact assessment to the Chilean authorities, which we hope will result into an environmental permit in the coming years, which will allow us to actually implement the technologies I mentioned you in our operations. The environmental impact assessment, according to the Chilean regulation, does not incorporate LCA methodologies. However, the insights that we are gathering also in this process will help us in the estimations of the footprint of how these technologies will influence the footprint in our operations. So I hope I gave you an overview on how LCAs fits into our strategy, and also the fact that it's not only a technical exercise, but has to be contextualized in the local situation, which I also find quite fascinating, because the technology might have all the right features in principle, but that has to work in the local context. So thanks a lot, and I hope to see many of you next week in Brussels for the Euro Materials Week.
Thank you so much, Andrea. This was indeed very meaningful, not only what you need from the industry side, but also what you do, in which way you operate, and many interconnections that you have shown with the work that we have done and we have discussed today during the webinar, including possible expansions, because of course in the previous presentations we have not covered all the aspects that are relevant to a big company like yours. We are a little bit late, but not horribly late. So I guess our connection will not be cut, isn't it, Ramona? So we can still leave a little bit of space for a few questions. Meanwhile, you Andrea, you are just calming down a little bit. No, I'm kidding. Of course, you are super calm, but you spoke until now, and so we go back a little bit to Luca with the question that was there. From Leila. So the question from Leila, if you can see the chat, you see that on your own, which is which kind of liquid waste you have started from.
Yeah, thank you, Leila, for your question. Indeed, the liquid waste refers to the European Waste Code for non-hazardous liquid waste coming from chemical surface treatment processes. And unfortunately, this is it. We know only this waste category, but no clue from where it's come from.
Great.
So, yeah.
And then the second from Jose Luis, which is about the large differences between primary and secondary, which is not unexpected, but a little bit of comment on that.
Yeah. Thank you also, Jose, for pointing this out. Indeed, we also try to understand if our results are reliable, and what we found is that 90% of the impact for primary metal production, at least for the precious metals, relates to mining and concentration activities, with the remaining more or less 10% attributed to purification and refining. So in this sense, if we consider the integrated refining plant we analyzed, we can compare the purification and refining from the mining industry to secondary production, which makes results more comparable, say similar order of magnitude. Actually, there was no time to go through it, but very recently the IPA, the International Association for Platinum Group Metals, released a report on LCA applied to the PGMs for primary and secondary production. And secondary production is, as mentioned, is comparable to what we got, but fortunately, the results for primary production are even higher than those estimated by Phil and MEC. I can share with you in the chat the link to this report if of interest for you and the other participants, in case you wish to get more information. But yeah.
Okay, yeah, we can see.
Yeah, unfortunately, this was released only recently, so after we completed the study. But the interesting point is that they also look at the year 2022, so somehow it's consistent in terms of time coverage.
Okay, thanks a lot. Now let's switch to Andrea. So we have a question on phasing out the ponds and going to direct lithium extraction. So what's your comment on that, Andrea?
Yeah, no, thanks a lot for the question. I think it includes a lot of elements. So maybe just for the background, also to explain a bit better regarding the Salar Atacama where we operate. So we operate in the salt flats. The local communities are located in the surrounding area, and they are located higher up on the Andes side, and higher up compared also to where we extract the water and where our water wells are located. So historically, they've settled in these locations because you have canyons and natural spring wells. Nevertheless, also for their culture and their hydrological cosmovision, water has a huge importance. So this links to what I was mentioning before about their approach related to water and to nature in general. So that's just for the background. And so we plan to reduce the size of evaporation ponds and use a combination of the technologies that I was mentioning before. So mechanical evaporation, membrane filtration, and also DLE. At the moment, we already reinject part of the brine, and we have already, as I said, achieved quite significant reduction. So it's progressive process. It's not that everything will be phased out immediately, and it's a process that will take years. So consider that we are submitting the environmental assessment next year. Then it will take some years for the authorities to give a permit, and then in the 30s, let's say, will be the time for the actual implementation of the technologies. I hope this helps.
We have another question for you, Andrea. I'm sure you want to pick the first part. I'm not sure you want to respond to the second part, but let's see how it goes. So over the last few years, the market price of lithium dropped by a factor 3 or 4 or something like that. So what are the consequences for a company like you? And what's the threshold for you to survive or to be happy with?
The price is even lower to what is mentioned by the question. I think it's half of it. Years also before the spike. So the spike was an exceptional moment. But if you look at the historical prices, at the moment is higher than what was some years ago. So we need to put into perspective also using a longer timeline than just comparing to the highest spike in the market.
I mean, the highest is super nice. I mean, business-wise would be perfect, a perfect gift for you, I guess. All right, I think it's about time. I guess we had a very nice conversation, very interactive, I would say, with the experiences from different TRLs, from different projects, from different perspectives. So I think that on all sides, we are part of the same community and we understand the importance of life cycle assessment and the fact that it should be meaningful also for the other partners. So if I can conclude, in projects like METALLICO, the life cycle assessment team is just one extra team that works together with the rest, and so it's part of the development of the technology. So it's not something disconnected that can just live or survive without the others. And at this point, it seems that also the others cannot live without life cycle assessment because they need to understand their environmental impact. And when it comes to industry, this is vital. And you have shown very well, Andrea, why this is meaningful to you and what SQM is doing. So I would, if you allow me, I would conclude on this type of collaborative environment because, well, otherwise I could conclude on methodological aspects, on the low TRL and the challenges. Maybe I could sympathize with Gyslain and Stefano that are suffering when they try to understand why these processes are changing so rapidly, and it's not really easy to understand how to translate what the other partners are doing into environmental impact. But I guess these are many of the aspects that we have touched. So if you don't mind, I declare victory for everybody, and then I think with many of you we'll see each other next week in Brussels, as Andrea said. So thank you so much for having contributed. Thank you so much to everybody. Anything to add, Ramona or Jana? You are in the end.
Yes, of course. I also want to thank you all for this vital discussion, and also for all your contributions from the speakers. Also a special thank from my side and from the KIMA side and from the METALLICO project to Gian Andrea and his team, to Stefano, Julia, Gyslain for the organization and to bring us all together here, and also to include all those different perspectives in this program of today. As you know, the METALLICO webinar series is a series, and therefore we have quite soon in February the next webinar, which will be about leaching and bioleaching. Today we heard also some results on leaching and bioleaching, so we would be very, very happy that you join the next time. And more details you will find on our METALLICO website and on our LinkedIn profile. So we would be very happy that you join. And so then thanks again to everybody, and I wish you a very, very nice afternoon.